Good afternoon, everyone, and welcome to this webinar on engineering manufacturing processes using advanced simulation technology. My name is Melissa. I will be your host for today. And with me is Igor, who will introduce himself in a minute, and he's going to present about the manufacturing processes. But before we deep dive into that, a short intro. So on the right side of your screen, you can enter any questions that you may have, and Igor will answer these at the end. And you can also reach out to us anytime on our email addresses, which will probably come into view in a bit. There we go. So yes, on the right side, you can ask any questions. So please do add your name so that we know who can follow up, who to follow up with. And then you can also reach out to us anytime. You can see our email addresses on the screen, and I will put them in the chat on the right as well. So feel free to reach out anytime if you have any questions. So just a short introduction for people who do not know us. I know there's a couple people from abroad joining as well. We're part of Summa. We are the exclusive business partner for Hexagon CAE for the Benelux. And so Hexagon has a lot more than just CE software. And today you are only going to see a small portion of just the CE software. But basically we have various other things that will be on screen in a minute as well. But just to get a short intro from your side as well, I'm curious to learn who is in the chat and what kind of processes you are using at the moment, what your company is using at the moment. So whether you're into stamping or forging, maybe even additive manufacturing, please leave that in the chat on the side and we can discuss a bit at the end. And we're also curious to know what kind of processes are you interested to learn more about. So if you're stamping at the moment, are you interested in looking at additive manufacturing? So yeah, just leave that in the chat and we can get a bit of an insight of who is in the audience today. So as I said, we're part of Summa, which is a reseller for Hexagon, and Hexagon basically has everything to do with digital reality solutions. Very globally put here on the screen, digital reality solutions that are empowering an autonomous, sustainable future by putting data to work. And as I mentioned, there is more than just CE software, and there is also a production software, so CAD, CAM, CNC solutions, and then also metrology and inspection, so for quality inspection, laser tracker scanners. And with that, you can create like a closed loop with a full digital thread for connecting engineering and manufacturing. So that is very briefly what Hexagon is about. So for this webinar, we are going to, as I said, focus on the design and engineering part, and more specifically, forming software. So with that said, Igor, would you like to start?
Yes, thank you, Melissa, for your introduction. Sorry for this short delay via Teams. I think you see a little bit delay in some of the slides, but hopefully from now on it will be a little bit more in line with the text. Of course, welcome everyone. It's nice to meet some of you and good to see some of you in this webinar. For today, we prepared two key points to share with you. I would like to start the webinar with giving you an idea about virtual manufacturing and costing solutions which are developed by Hexagon using some kind of a real-life example. And after that, I would like to go into a more specific subject, which is all sorts of application examples, manufacturing processes and simulation of manufacturing process, specifically looking into the forming technology. Keeping in mind the size of the group, we thought that maybe it's the best idea would be to ask all of you to keep your questions up to the end of the webinar, and then at the very end we'll have time, as Melissa suggested, for questions and answers. So to introduce virtual manufacturing and costing solutions from Hexagon, I thought that would be nice to show you a real life example, such as electric vehicle battery, which is a quite complex component, which comprises of multiple subcomponents or multiple products. So it's a complex assembly where you utilize all sorts of manufacturing process to be able to produce the part or to produce the components, and then to assemble components together. And then, of course, if you think about electric vehicle battery, then you have all sorts of issues related to, or challenges related to manufacturing of individual components or final assembly. You can think about long development time, which could be related to missing data at the right moment in time, or some assumptions made just because the right data is not available during the engineering of the process. You can think about all sorts of quality issues, like you manufacture a product or a component, and then you see that it's outside of the specification tolerances and something needs to be done about that, maybe tuning the process or applying some kind of reworking, sometimes even manual reworking. You always have some issues with the engineering changes, for example, late changes in the material specifications because some material is not available or cheaper, or maybe changes in the geometry. Then you have, as always, a challenging thing like stability of manufacturing processes. You can develop a process and you think that everything is fine, but as soon as you start production, then maybe after 1,000 or 10,000 parts, something happens, and then you have the next 100 parts which are just scrap, which are outside of the specification requirements again. And you have all sorts of questions in mind. How can it happen? What influences that? And what is the main driver of this instability? Then you have material waste and, of course, tool life, which means that a lot of maintenance on the tooling or on the tools used in the manufacturing process, and lots of time and money wasted. If you think about this, these challenges are not really specifically tuned for manufacturing of electric vehicle battery. It could also be seen as a sort of like a global list of challenges you're always facing during manufacturing of any type of component. And to be able to support and facilitate the development of high quality manufacturing processes, Hexagon developed virtual manufacturing and costing solutions which can be applied at different moments and different stages of development. Starting from early feasibility analysis somewhere during the conceptual development, during the component design, going all the way into the engineering of the manufacturing process, maybe it's a forming process or any other type of process, and after that going into the assembly and final, let's say, joining of the components to make the final product. So the solutions from virtual manufacturing and costing from Hexagon can be used at any moment of the development cycle. And to give you some more specific ideas, if you think about early conceptual development phase, you can maybe isolate two specific components from the electric vehicle battery, these outer shells, which are made of sheet metal. So typically you would want to stamp them, and stamping process, you have a lot of challenging things there, so that at the beginning during the process development you can apply the simulation software to improve the utilization of the material, to perform the correct nesting of the blank, for example, within the coil to save the material. Then you can think about using simulation technology to facilitate the process planning and estimation of the number of stations you need to produce the part. And of course, you can apply all sorts of tools to estimate the tooling costs per station and maybe minimize the tooling cost per station. And then, of course, you can look into simulations supporting decisions making with respect to whether the process is of good quality or not by looking maybe at the risk of splits or thinning in the material, and then making decisions there what to do, maybe tune the process or maybe change the material or maybe change the geometry. So the simulation technology can be used as early as this stage to facilitate all sorts of changes and to make the right decisions at this moment in time. And then if you go further, moving on into maybe engineering of the manufacturing processes, if you isolate a single component from this entire battery assembly, you can think about maybe one battery cell where you have a small cap which has to be formed. It's probably going to be made from, again, sheet metal. You're going to somehow maybe stamp it, and then using the simulation technology can give you an idea whether the process is well designed or not, and what to do to improve maybe the thinning distribution, to account for all sorts of coining effects in the process, and then to have high quality part. If you think about any other component from the entire assembly of the electric vehicle battery, maybe again another battery cell, then using simulation technology, you can optimize the rolling process where you are trying to, what you can see from the animation, where you're trying to maybe look into development of the process where the outer case of the battery is formed on top of the previously formed cap. And here you're applying rolling technology with a certain number of rollers, and you can think about optimizing this process somehow, maybe minimize the number of revolutions, or maybe look into the number of rollers which needs to be used here to be able to produce high quality part, and how to reduce the cycle time. That would also be one of the questions you can answer using the simulation technology. Then if you think about the battery housing, which is another, let's say, component in the battery pack, could be produced by backward extrusion, which is a type of the cold forming process where you actually form this case using the typical extrusion process in multiple stations. So here, instead of, let's say, rule of thumb, you can apply simulation technology to understand how many stations again do you need, what would be the geometry of the tools per station, how to guarantee the uniform flow of the material, how to get a uniform distribution of the thickness of the material of the entire housing, and what would be the end boundary of this housing after the complete process, so that you can apply the cutting and trimming operation to the right height. So all sorts of questions like this can be answered by, again, using the simulation technology. The battery housing itself would have a cover, and if you think about the cover, again, maybe stamped from the sheet metal, stamping of the sheet metal, looking at it once again from a different perspective, so not from the perspective of feasibility or risk of splits, but looking into the shape deviation, which is caused by or might be caused by springback. So if you simulate the process, instead of doing a trial and error, you can think about how to minimize, for example, springback, maybe changing the process conditions, tooling forces, etc., to introduce additional stretching of the material to reduce the amount of springback. So all these things are much easier if you have simulation technology at hand. Then moving on to assembly of some components, so let's say early assembly of some components of some sub-assemblies. The cover of this housing would be connected one way or another to some kind of connectors, which are then used later on, let's say, which are needed there for the functionality of the entire product. And these connectors are normally attached to the upper cover using some kind of mechanical joining technology, which is in this case clinching. You can simulate clinching, and you can try to analyze what kind of geometry of tools do you need to have to be able to get the optimum mechanical joining with reasonable interlocking, maybe how to increase that interlocking to have a strong connection, strong mechanical connection, and then maybe do some kind of optimization loops here to be able to understand what would be the most optimum geometry of the tools in this case. After that, you can also think about applying the simulation technology to look into the further mechanical joining techniques which are used to assemble some components, which could be riveting, where you have a rivet penetrating through the thickness of two materials which are being joined together. And simulating this will give you again an idea of how strong this mechanical joining is, or mechanical join is, and what kind of interlocking you get by using a certain geometry of the rivet and how to improve it. And then going all the way back to the final assembly of, in this case, again, still of a subcomponent, you can apply the simulation technology to understand the impact of welding. When you try to weld maybe outside this outer housing to the upper cover, then you can simulate the welding process. You can try to understand what happens if you apply a certain amount of heat in a certain area, how that impacts the distortions in the final sub-assembly, what kind of deviations from the nominal geometry you will have. And then you can also look at the temperature distribution to see whether that will have an impact on the quality of the final part. And then, of course, you can try all sorts of different types of processes. For example, you can think about using special clamps like you see on this slide, which have some kind of integrated, maybe active, maybe passive cooling. So you can run a relatively sophisticated simulation where you have an idea that specially designed clamps which can be used in this process can improve the entire situation, and then can improve the conditions and can eliminate or reduce the distortions you might have at the very end of welding. So all these solutions, all these products, they belong to the virtual manufacturing and costing solutions from Hexagon. And what you have seen so far is welding solution, forming solution, or solutions which can be used for early feasibility studies, for costing, for process planning. But there are also other solutions like additive manufacturing technology or simulation technology or topology optimization, generative design, and some optimization tools for the mechanical joining technologies. So all these comprise the virtual manufacturing and costing solutions from Hexagon, and during the development of these solutions, we always keep in mind that we are trying to provide some tools which could be used to accelerate digital transformation and to improve the manufacturing quality, reduce cost, and reduce time to market. For our webinar today, I would like to focus on forming only. So today I would like to look into the forming technology, and just to give you an idea, using some use cases, I would like to show you what you can do with the simulation technology to facilitate development of some forming manufacturing processes and how to improve their quality while eliminating all these unnecessary tryout loops. Simufact forming is the tool which is used to simulate all sorts of forming processes, and this is the technology we would normally use to simulate bulk metal forming, to simulate sheet metal forming, to simulate mechanical joining, and maybe some processes where you have relatively complex kinematics like roll forming or re-enrolling or stretch forming. So if you look into every specific field, maybe one by one, and then checking some use cases, maybe starting from hot forging, then you can simulate all sorts of hot forging processes, which could be upsetting technology, bending, trimming, multi-directional forming or forging. And the simulation allows you to set up a rather sophisticated process with realistic number and the realistic types of the operation steps, like heating the blank, transport from the oven, preforming, maybe in multiple stages, and then final forming. If you think about the solver behind this simulation technology, it is quite sophisticated, because what you have in terms of the material flow, maybe in this flange area, you can see a lot of material which is either splitting or overlapping. So the solver which is used to simulate hot forging type of processes is quite robust, and you can have all sorts of overfolds or material folding onto itself easily simulated without any kind of numerical issues, and you have a good estimate what happens with the flow of the material at any station of the process. The simulation itself is also quite sophisticated, so you can you can run a coupled thermomechanical analysis where you have again thermal effects impacting the behavior of the material and the mechanical behavior of the material and the flow of the material. If you are into this hot forging, and if you're engineering the these type of processes, you can think about using the simulation technology to find suitable geometry of the tools at any intermediate station, or maybe you can also estimate how many intermediate stations you need to have to be able to actually manufacture a quite high quality part. You can think about analyzing typical defects, such as, for example, faults or not sufficient fillings or under fillings you can find in the final part. And then one other step you can make if you want to make this simulation a lot more sophisticated is you can introduce deformable tools, and you can actually estimate what happens in the process with the deformation of the tools as objects, and what kind of stresses you develop there, and then whether those stresses will lead to any kind of cracks or issues with the usage of the tools for a certain period of time. And then, of course, the typical benefits. I think I have this type of slide only once, just to give you an idea what kind of benefits you can get from the simulation technology. Most of these benefits are obvious, and then they will be also relevant to all other processes. Simulation tool can help you to reduce the material usage, obviously, to reduce the scrap, to reduce the material waste. You can think about engineering the right processes, which are actually quite robust, and that means in the long term, that means correct usage of the equipment you have and correct usage of the machine, so you don't have any idle time to resolve all sorts of production issues in the future. And then, of course, if you do everything correctly in a simulation, then you can extend the life of the tools so that they don't break after a certain number of cycles. And then, of course, overall quality of the product can be improved if you have a simulation technology which is used early on during the process development. Another type of processes, you can bulk metal forming processes, which you can simulate using Simufact forming, would be open die forging. You have here a nice animation showing you that you're actually forming a complex shape in a number of strokes. So starting from some kind of a rectangular blank of a certain dimensions, which is also heated blank, using some kind of greepers which rotate and translate the part, and using some kind of tools which have normally simple geometry, flat shape, or maybe a slightly curved shape. In the number of strokes, you can reform that into a certain product, which can then be further on post-processed to obtain maybe some final product. Once again, for open die forging, what you can think about is you can set up all sorts of processes, including rotary forging, radial forging, shell forging, etc. So you can actually define relatively complex kinematics of the tools, and you can specify all sorts of process conditions which correspond to those specific processes. And the nice thing, what you can get if you, or what you can rely on if you use the simulation, is all sorts of preprocessors which are built to facilitate the input, to facilitate the process definition. So if you have if you have simple kinematics, it might not be necessary, but as soon as you have some kind of, I don't know, rotations coupled with translations, some kind of grippers which are applying certain forces, etc., it makes sense to have some special preprocessors which are available to speed up the process definition and to make the life of the user a lot easier and faster. And then what is also interesting here is that to simulate, in order to simulate the open die forging process correctly, you can also think about taking into account the shape of the blank, of the initial starting blank, which is coming from the casting itself. So you can actually couple this open die forging simulation to the input, which is then provided from a simulation of casting, maybe coming from Magmasoft or Procast, and then you can utilize the actual shape of the initial blank with maybe some kind of imperfections inside or geometry imperfections in the actual blank. You can utilize that to have a rather sophisticated process of open die forging. The typical usage of the software would be that, again, you apply it at different stages of development. Maybe initially you look at suitable kinematics, what the grippers will do, what kind of translations you have, etc. How many strokes do you need to be able to produce something? And at the later stages of development, you can think about validating or evaluating or estimating the typical defects, such as, again, all sorts of underfillings or cracks or high areas with high stresses, which might lead to all sorts of issues. And then again, if you have a coupling to the results coming from the casting simulations, you can also estimate what happens with those defects which are present there, where the material is not fully filled, and what kind of evolution of those defects will be if you go on with the forging process. Going into cold forming, which is then another type of bulk metal forming technology, which is then used to produce all sorts of complex geometries, like you see on this screen, some kind of fasteners. Simulation can be used to validate all sorts of processes, for example, upsetting, wire cutting, radial forging, etc., etc. And then you can again define a very realistic process where you have multiple steps, multiple operations, similar to what you have in reality, maybe in addition to several intermediate stations to give a certain shape to the final to the product. You can also add some other operations like annealing, where you reset the stresses and strains in the material and then continue with a sort of like a reset material with the further steps. And then also you can, at the end of the entire process, you can define an operation which could be a final heat treatment operation to give some specific mechanical properties to your final product. So the sequence of steps you can define can be anything what you can find in reality to really help you simulate the process as real as possible. And then, of course, here again, to facilitate the process definition, you can find all sorts of preprocessors to help you define the parameters as you would define them in the actual machine, so that you have the right kinematics and the right process conditions. What the simulation can also do for you is maybe one interesting thing is that, yeah, of course, early on in the process, you can try to find suitable kinematics of the tools. You can maybe work on multiple concepts to see what happens if you have that number or that number of stages. But what you can also do is you can predict the distribution and the evolution of the grain fibers, what you can see here on this picture, which actually indicate how the material flows during the cold forming process itself, and whether this flow is uniform, whether you have some issues or defects, or you have some kind of strange interlinking of these grain fibers, meaning that most likely you will have some kind of a critical area with high stresses or potential for cracks, etc. All sorts of defects you can find in cold forming, again, unfilled sections, overfolds, cracks, all that can be analyzed, including obviously tool forces, which can then also be used to estimate how the die is performing, whether there are some issues with the failure of the die in the process or any kind of potential issues further on with tool wear. For the more complex kinematics, so going further from the bulk metal forming into the processes which have sophisticated kinematics. If we look at the rolling type of process, you can actually simulate all sorts of complicated kinematics. For example, here, if you look at hot rolling, where you have a cylindrical blank pulled through the set of rolls. These rolls will have a special geometry, and then when the material is pulled through the rotating rolls, then you give this geometry to the final blank. You form it in some way. So these type of processes could be easily simulated, including the cross wedge rolling, where you have again a special geometry in the rollers, and if you look at maybe some kind of front view, you're looking at some kind of cylindrical blank, which are now formed by the rollers into a more complex shape. These type of processes can be set up and can be simulated to obtain or to estimate the typical defects and typical process conditions. Some other examples could be sheet metal roll forming, where you pull the material through a set of rolls, forming it into a complex profile-like shape using quite a large number of rolls. So here again, you need to have special preprocessors to define the rollers, to position them correctly, to define the correct kinematics, etc., etc. And here you can also work with 2D input coming from AutoCAD-like program, where you actually define some profiles, which are cross sections of the rolls, and then you can utilize that directly to define the geometry of the rollers. And then maybe one other example which I have here is this cross-profile cold roll forming, where you have rollers which have some kind of special geometry. It's like a stamping process, but then using rollers. So you have two rollers. One of them has the cavity, one of them has the embossment. They're obviously synchronized. So when you roll them, or when you pull the material through this set of rolls, you are forming these embossments on the flat sheet in a sequence. So this process can also be simulated, and the typical benefits you can get from the simulation would be estimate process kinematics or tools kinematics, estimate the position of the tools, find the right shapes of the tools. That can be quite a difficult process if you don't have simulation technology. It can take you quite a lot of time to really tune the process conditions to be able to have high quality parts. And then, of course, you can look into the shape of the part, look at the deviation of the shape of the part from the design specifications, from the CAD geometry, and see what you can do to improve that. Another type of rolling process, one nice thing what I forgot to mention here is, of course, the roller stand stiffness and roller deflections. You can make the rollers to be, if I, let's say, roughly speak about that, force controlled, so that you can define some kind of a stiffness and some kind of limiting force, which means that if the blank reaction forces are so high that the rollers are lifted, they will be lifted. which means that you have all sorts of deviations from the intended process design, which means that you are not able to obtain the final shape of the part. So that's something what you can define also in the process to make the simulation a lot more sophisticated, this roller stand stiffness and the even deflection of the rollers, to estimate how the gap between the rollers is changing due to the forming of the tool of the blank and due to the reaction from the blank material. Re-rolling is another sophisticated type of the process in terms of the kinematics. You can set up a simulation of all sorts of processes, such as radial re-rolling, radial axial re-rolling, which is this raw process you see here, where you have a set of rolls which are then acting on the blank in radial direction, but also in axial direction, to form it into a different type or different shape of the ring. You can also simulate this MRV type of processes, multi-mandrel radial processes, where you have different mandrels having, again, very complex kinematics forming the ring object on the outside and also on the inside, and also changing the diameter at the same time, so that you can get the final product using this technology. These rings obviously can be quite huge depending on the application and depending on the usage in reality. The simulation itself is can be run as a fully thermomechanical coupled simulation, where you have also thermal effects and you have all sorts of operation steps you can define, starting from the original blank going into a number of pre-forming steps and ending with the final forming step. And again, if you think about kinematics of, for example, this process, it can be a nightmare to define it manually using maybe, I don't know, general purpose code or in any other simulation tool. In Simufact, you have all sorts of preprocessors to say that you will have that number of rollers, they will have that that specific movement in along X direction, or that specific rotation, and you can easily define the process using process conditions which you would have in a real equipment, or coming from the real equipment, coming from the real machine. The typical gains you as a engineer who is trying to design any manufacturing process, typical gains you can get here are similar to the previous one. Again, you can estimate all sorts of concepts and look at the quality of the final part. Then, looking into rather specific type of processes, heat treatment, in Simufact forming, you can define quite sophisticated heat treatment cycles or heat treatment processes, where you can, for example, analyze quenching operation, or you can do case hardening. I have two animations here which actually visualize both. So for the quenching operation, what you see here is some kind of a typical test which is used to estimate the let's say quenching potential of the material somehow, or to estimate the phases you get in the material and mechanical properties. So what you can see here, after heating it to austenitic temperatures, you get some cooling cycle applied with a certain cooling rate, and you get phase transformations there. You have certain amount of martensite formed, and you will have certain in some areas, and you will have certain mechanical properties because of that specifically chosen cooling curve or cooling cycle. You can also simulate case hardening, which is then changing the mechanical properties of a final product. So now we're talking about really a final product, where you can apply this inject a certain amount of carbon into the upper surface of the final product, and after that you can apply some kind of a sophisticated thermal cycle to get the correct right properties, mechanical properties of the final product. So even this type of processes can be simulated in all sorts of ways, with all the stages there, with this injecting the carbon, diffusion, applying the thermal cycle, and then looking into the final properties of the material. So the sequence of steps you can define in any heat treatment process can be quite also sophisticated. You can think about the heating operation step, holding, transport, cooling, reheating, etc., etc. And you can follow here different solution strategies based on CCT and TTT diagrams to obtain the final phases in the material and also to estimate the final mechanical properties. You can use the simulation technology to validate or maybe also design your heat treatment cycle. You can predict the mechanical properties in the final part. You can look at the phase fractions and also estimate what does it mean to apply a certain heat treatment cycle. So what is it? What kind of impact it has on the stresses and distortions you get in the final product, and how big the deviation will be from the CAD geometry from the intended design. Then going further with the mechanical joining, which is then another type of technology, could easily be simulated in Simufact forming. You do this simulation on the coupon level, estimating this process itself. So you're looking into the area of a mechanical joint where it is applied using some kind of realistic tool geometries. That's more or less the scale of the problem you're trying to solve. And then, of course, in addition to that, you have the possibility to simulate virtual pool testing. I'll have a picture about that, or actually animation about that. So that's the level where you're staying to estimate the mechanical joining. The simulation technology can be used to estimate all sorts of methods, punch riveting, self-piercing riveting, clinching, and even high speed or high momentum joining. You can also apply, do an analysis of what the adhesive is going to do in the joining zone. And then again, here you have, especially here also, you need some special preprocessors to facilitate the process definition. The simulation can easily be used to predict, for example, failure in the tools or in joints to find the most optimum joining parameters, sorry, not joining parameters, but geometry of tools to get the most optimum joining parameters like interlocking and the forces. And you can also analyze the behavior of the material during the joining process itself. And you can also actually estimate robustness of the process by looking into what the variation of the material properties or process conditions will do to your interlocking or to your joints. To give you an idea, maybe also just one case study done together with one of the universities in Germany, if I'm not mistaken, simulation of self-piercing rivet, where you are actually trying to join here two different materials using this rivet and analyzing the simulation results, comparing that to reality. You can see a nice match in and interlocking between simulation and reality, and also this bottom thickness, how much of, let's say, actual material is still there under the rivet. So you can estimate it in the simulation, obviously, and you can see good, well-matching results with the actual measurements, including also realistic force evolution, which is quite comparable also to what is obtained in reality. Virtual testing can be done based on already joined components or mechanically joined components. You can actually pull these components aside or out in a certain direction to be able to see how strong the joint is and under what condition, under what level of the force it will actually break. And you can apply this, you can simulate this pull test in all sorts of configurations or in all sorts of directions, monitoring the evolution of the forces. And then what you also need to think about is that it's not only about a single geometry of the joint, single spot-like analysis. In Simufact, you can also find a tool which is called joining optimizer, which is then used to help you decide on what kind of joining technology and what kind of parameters do you need to use at different areas of your assembly. That could be interesting if you have a relatively complex assemblies. Maybe this is an exaggerated example of the body in white, where you have all sorts of materials which should be joined together using mechanical joining techniques. So to help you decide on what joining method you use, you can use the joining optimizer, where you specify the types of materials you're going to join, how many of them do you want to join, and the thicknesses, and then running some kind of estimator using optimization technology, you can get some suggestions on the type of the mechanical joining technology you should use, on what kind of geometry of the tools you should use, and your this is all based on your user-defined targets for the interlocking and for the, for example, the forming forces you would like to have in this joining operation. Then sheet metal forming could be done using Simufact forming, where you can simulate all sorts of processes like stamping, ironing, fine blanking, stretch forming, tube bending. What you can see here is a simulation of draw die reduction type of processes. So where you have a cup which is formed in multiple stations, formed and reformed multiple times to obtain the final product, which is a lot deeper than the initial shape. And the nice thing about the simulation is that you can easily switch between the 2D analysis, where you use the 2D plane strain elements to capture all these 3D effects, to capture the ironing and coining, and then you can easily switch to 3D analysis, where you have a full blank, and then you can estimate the shape distortions due to spring back. You can define relatively complex, again, tool kinematics to be able to support your processes, and again, you can use the simulation as a tool to estimate all sorts of concepts of the process and to predict typical defects like thinning of the material, failure, wrinkling, spring back, etc. To give you some other examples of the processes related to sheet metal forming, one of them would be fine blanking, what you can see here, where you're actually holding the blank in between the tools, and by using certain set of tools, you're actually slicing through the material, obtaining this or simulating this blanking operation. These type of simulations could be done using geometrical cutting, where you say, okay, there's the geometry of the tool and I just slice through my material, or you can do a sophisticated simulation where you can say, I apply some kind of a damage model and I estimate what happens in the area where the blanking is done, using certain geometry, certain gaps between the tools, what happens with the evolution of the shape of my sheet based on these damage models. So that can be quite sophisticated simulation of fine blanking. And then what you see here is one animation I borrowed from Hexagon, Simufact Hexagon LinkedIn profile, which shows you prog die type of setups, prog die type of processes, which is used for making connectors from the electronics industry, where you can see that you have multiple bending operations, trimming operations, forming operations, and then final, let's say, forming operations, where you sometimes even fold the material onto itself, having a contact there between the different areas of the material. So this is all supported by Simufact forming, just to give you an idea about the process conditions, most suitable process conditions to get the high quality part. And here is another example of tube bending, where starting from a certain geometry of the tools, of these grippers, mandrels, you can form the tube into a certain shape by having quite complex kinematics, and the simulation can give you an estimate of all sorts of wrinkles, collapses you can have here during the actual forming process. Hot forming processes could be simulated. Typical hot stamping or hot forming process could be simulated using regular tools, regular kinematics of the tools. And in the simulation itself, you can estimate the distribution of the temperature in the sheet, the heat flow. You can define the tools which have 3D geometry, which have cooling channels, which have heat flow from the sheet to the tools, from the tools to the cooling liquid. And you can have a sophisticated simulation to analyze phase transformations, distortions, and microstructure evolution in the final product. And I think now this brings me to maybe the final part of my story regarding the forming process, some kind of special analysis or types of the analysis you can do using Simufact forming. For almost, I think, for any process, you can always define the tools to be deformable. So you can define the real 3D geometry of the tools which are used in the process. Here you're looking at some kind of a cold forming process where you have sophisticated tools, and maybe this upper and lower tool are having the actual geometry defined and they are really deformable during the process itself. So you can run this type of analysis to see what the forming process will do with your tools, what kind of contact stresses are developing between the tool and between the blank and the tool, and what does it mean in terms of the stresses developing in the tool itself, in terms of the risk of cracks, etc. So you can run this type of analysis to estimate behavior of the tools, and also to look at the elastic deflections in the tools. And the approach here could be two sides. So on one hand, you can do a fully coupled analysis where your tools are deforming together with the blank. So from increment to increment, you are looking at the deformation of the blank and deformation of the tools. And you can also have a somewhat faster analysis where you say that at a certain point in time, when maybe I close my upper tool and the lower tool, I get the contact stresses which are acting between the blank and the tools, and I apply those contact stresses to estimate the stresses and the deflections of the tools. That is a lot faster analysis because you only do it once or twice at a certain point in time, and then you can get an estimate on the behavior of the real 3D tools. And then, of course, you can also apply you can also do analysis with the heat flow in the tools and the temperature distribution. Another thing you can do with that is the die wear analysis based on the contact pressure, relative velocity between the blank and the tools, material properties, cycle time, number of strokes. All that can be used to estimate the wear in the tools, and you can apply that or do this type of analysis for rigid and deformable tools. So here you have some kind of an estimate of the wear of the tools in case of a cold forming process. And you can have a nice distribution of, let's say, critical areas where most of the wear will be localized. And then for damage prediction, you can have all sorts of models. To be honest, the list is quite long. And the reason behind is that there are so many different types of processes that different models should be used to estimate certain damage phenomena in the final products. And you can use any of these models, provided that you have the right parameters. You can use any of these models to estimate the failure or damage, to look at the evolution of the damage. And again, both types of approaches are available. You can have an indicator type of model where you can actually predict the amount of failure you can get or damage you can get, or you can say I couple fully my damage to my analysis, and then I look at the changes in the properties of the material during the process itself. So you can have two types of approaches here which can easily be simulated. User subroutines are available. You can define all sorts of user-defined subroutines to have even more advanced tool kinematics, to have even more damage models, to define different material laws, friction laws, and to change or maybe to have your own post variables. And what you see here is the user subroutine, which is actually estimating the evolution of the roughness of the blank formed by two tools, and what happens with the roughness of the blank during the actual forming process. And then the last thing is, at any moment in time, you are supported, especially if you go for complex kinematics, you really have a process-oriented user interface, which means that you have all sorts of templates there which help you to define the kinematics, to define your equipment, and to define the right process conditions. So that's something what is quite unique, so that you don't waste too much time on doing some kind of strange definition of strange conditions, which never happen in reality. This is trying to be as close as possible to what you see in real machines and real equipment. And I think that brings me to the end of my presentation. So thank you very much, of course, for your time today, for listening, for participating, and then we have not so much, but definitely still some time to answer some questions.
Thanks, Igor. I think we've all seen a lot of processes today. So, as mentioned before, there are many more processes that we can talk about, even like welding, additive manufacturing, and on the topic of welding, we will soon hold a webinar on that. I think we'll send out an invite for that probably next week. So that's something you can expect. And if there are any questions, I'm looking at them. There are some incoming, and if you have any more questions, feel free to send them now. Let me see, we have some time for a couple. Someone is asking about experience and your experience with products, but then also what kind of experience would people need, like training. And I'm guessing that depends on where you're coming from, whether you're from manufacturing or whether you're already experienced with CAE. So it's something you can elaborate on, Igor?
Yeah. What you normally need is a training, obviously, into the user interface, so that you have a little bit of understanding where to find yourself, and how to set up a process, how to set up some kind of conditions, numerical settings, and the running a simulation. But the good thing of Simufact in general is that it's really process oriented. So you don't need to have a numerical experience or FEM experience to run simulations. You just need to have a little bit of understanding of the process you're trying to simulate, and importing the CAD geometry, you can continue. So some training in terms of the usage of the user interface, but lots of the things are having default values, so to speak. So Simufact is using Mark solver, and that means that you have a lot of flexibility, but of course also lots of potential sources of errors. So to eliminate these errors, there are lots of default values you don't really need to dive into.
Clear. So it really speaks the language of the
correct,
the
yeah.
engineer, the shop floor.
Yeah.
Okay. Let me see. Yeah, can you tell me something about the applications and what way are they validated? I think we saw a couple applications from customers. Can you tell me a little more about that?
Maybe I can, depending on the question and maybe depending on the application, I can look around to see what would be a nice validation case to share. But obviously, there are lots of customers of Simufact, in Germany, in the US, where you have validation studies, even published ones. I have seen one recently from Schuler, if I'm not mistaken, where depending on the technology, cold forming or hot forging or whatever, somebody would compare results with reality, and you definitely have a nice match there. So maybe if you want to just send us an email with the question, what technology you're looking into, and then we can check whether we can have some kind of a case study to share.
For sure. I think there's plenty of material available, as always. I've got a pretty long question, which might be something to follow up with later. I don't see who it is from, though, so if they can please put their name so we can more easily follow up. It's quite a long question here. Let's see. We can do a final one, and then we can round it up. Yeah. So you mentioned also something about Mark, and then there are other software. There are users here from other software. In what way can they be chained with other software from Hexagon, for example?
What I think that's one of the key advantages of Simufact, that if you have different types of processes, that's not really a big issue. You can define always your initial blank to be coming from any process. You can transfer the results calculated or history of, I don't know, stresses and strains coming from a different type of process. You can use that as a starting point in another type of the process. That's always possible. So you can have really complex chains of realistic manufacturing processes where the data are transferred from one stage to another, and you can benefit from that. Maybe that was the correct, the right answer to the question. Yeah.
Okay. I found out who the long question is from, and I think that's best to because I see we've also run out of time. So to respect everyone's time, you can always send us an email. The emails were on the screen, and we will of course follow up with a recording also, and invite you for the next webinar on welding soon. And as I mentioned, anything you would like to know more about, any process, and also processes that we did not discuss today, always welcome to reach out. So thank you. And thank you, Igor.
Yep. Thank you, Melissa. Thank you all for your time.
Thank you.
And
see you soon.
yep. Have a good day.